This video is on using the first derivative in calculus. Let's start off with a definition. So, for a definition here, a function f of x is increasing on an interval if a is less than b, then f of a is less than f of b. So it's a definition for increasing. You've probably heard of increasing before and probably have an understanding of it. What it's really saying is, for a function to be increasing, if I have an x value that's less than another x value, then the y value associated with the first one should be less than the second. What that does is it causes to rise from left to right. A small little sketch kind of showing this, just so you can kind of see it. This is x and this is y. Here's this function I'll call f of x. We have, here's a, this point would be f of a, here's b, this point here would be a y value of f of b. So what it's really showing here is that, if a is less than b, then f of a has to be less than f of b in order for it to be increasing, rising from left to right. Similar but different, a function f of x is decreasing on an interval if a is less than b, then f of a is greater than f of b. In other words, a is less than b are the x values, and what it's saying here is that the y value associated with the first one is larger than that associated with the second one. So decreasing meaning moving downward from left to right. If I was to draw a small sketch of this like I did above, here's x, here's y, we could have a graph that kind of looks like this. Here's a, here's b, the y value with this would be f of a, the y value here would be f of b, and it's just showing that for a, f of a is higher than for b's f of b, the y value. So you're looking at, for decreasing, moving downward from left to right is the easiest way to think about it, but that's kind of the formal definition. Let's talk about how this relates to the first derivative. So for this theorem here, for a function f of x, if f prime of x, remember f prime of x is your first derivative, is greater than 0 over an interval, then f, the original function, is increasing on the interval. And this would make sense. First off, we're talking about an interval, so it doesn't mean the entire function's increasing, just on a specific interval. The other thing to note, though, is that when I say f prime of x is greater than 0, what I'm really saying is f prime is positive. And remember, the derivative gives you the slope of the tangent line at a point. So it's really saying if the slope of the tangent line is positive, then the original function is increasing, which kind of makes sense, Because, if it's positive, its positive slope is moving upward from left to right, so the original function should be increasing, So the derivative gives you information about what the original function would look like. If, similar but different, f prime of x is less than 0, meaning negative, over an interval, what do you think would happen? Well, it's telling you you have negative slopes to your tangent lines. So negative slopes to your tangent lines means it's going to be moved downward for the original function. So then f is decreasing. On the interval. Right, so if f prime of x is negative, the slopes are negative. A negative slope tells you that the original function is decreasing. You know, a little chart that I kind of make for myself that sometimes is helpful for people. If I write this as, here we have f and here we have f prime, and then let's talk about, you know, starting filling in for f prime, I'm just going to say if it's positive or if it's negative. If f prime is positive, it's a positive slope that tells you the original function f is increasing. If f prime is negative, it tells you you have a negative slope, so that tells you the original function f is decreasing. And this might be helpful a little bit later when we go to graph these, but just so you have it there now. So this is something you should know. You should memorize it, but you should memorize it, you know, logically. I don't think it's something that you have to memorize straight fact, understanding that if f prime represents the slope of the tangent line, a positive slope would tell you the original function is increasing. A negative slope would tell you the original function is decreasing. Let's just take a look at a small example here. Let's make sure we understand the intervals we're talking about. So for this example, I'm going to give you a graph. So if I said given, and I'll draw it out. So here's an x-axis, here's a y-axis, and we'll draw some function which I'll call f of x. All right, so this function is f of x. And I'm going to call this first point here A, the end point here B. This is the x values. And I'll call this point in the center here where it flattens out, I'll call that x value C. So, you know, if you notice, right, if we're looking at this, where is this increasing and where is this decreasing is really what the question is going to be. So f of x, the original function, right, where is this function increasing? Well, it increases, where is it moving upward from left to right? Well, it's increasing basically from wherever C is here to all the way over here. So we're talking about the x values where this happens. So f of x is increasing on the interval, right, I'll say on the interval from C to B. And notice I don't use the endpoints when I talk about increasing or decreasing. I'm just talking about the intervals where it happens. So from here, right, to here, it's increasing. At the actual points, it's not doing anything. It's over the interval that it's increasing. Then, what can you tell me about the first derivative? Well, if this is increasing, the slopes of the tangent lines will be positive. So f prime of x will be greater than 0 on the interval from C to B. So sometimes you can use the original function to tell you what the derivative sign will be, right? If this is increasing, the first derivatives are going to be positive because the slopes of the tangent line there will be positive. In a similar way, the original function f of x is decreasing. Well, where is this decreasing? Well, it's decreasing from the starting point here, A, up until C. So it's decreasing on A to C over that interval. Remember, these are the x values. And we don't include the endpoints when we're talking about increasing or decreasing. Then, tell me about the first derivative there. Well, the slopes of the tangent line, if it's decreasing, will be negative. So f prime of x is less than 0 on the interval from A to B. So in other words, right, the slopes of the tangent line are positive if the original function is increasing. The first derivative is negative if the original function is decreasing. And you should know that. I mean, this is just more of an instructive example so you can see it here. But that's really, you know, how we're going to use this between the first derivative and the original function. What are the relationships? Notice right here on this picture that I drew. At C, you know, it's neither increasing nor decreasing. It kind of flattens out, right at that x value of C. So we have a name for this. You know, we'll talk about it in a couple different ways. But, you know, this is going to be a critical value. And for our definition for a critical value, and it will say a critical value of a function f of x is any number, which I'll call c for now. Later on we won't be calling c, but any number c such that, remember this is an x value, such that either f prime of c equals 0 or f prime of c does not exist. So it's really where the derivative equals 0 or the derivative doesn't exist. And you know, when I say that, if you're looking at this picture above, f prime of c does equal 0 here because the slope of this tangent line is 0, right? The slope of the tangent line at c is 0. So we would consider this to be a critical value. And we'll talk about how we use it in a minute. But you know, that's going to be important to look for. So where the first derivative equals 0 or where the first derivative doesn't exist, right? So if you found that it was undefined at a point, that would be a place where a critical value would occur. So just a quick note, just to make sure we know what we just said. All right, so this note is going to say that really what I just said out loud. Critical values occur when the slope of the tangent line is 0, right? Meaning that tangent line will be horizontal, or when it is undefined. Right, so when the slope is 0 or when it is undefined, that'll be when you have critical values. And you know, something to notice here, and then we'll write another definition. If you're looking at this graph, right, this went from being f prime would be negative on the left of this because it's going downward, it's decreasing, and then it went to 0, and then it went to positive. So when you go from negative to positive in terms of your slopes are negative and going to positive, you have 0 in the middle there. It's really showing you you're going downward then moving upward. It actually shows you where you have a minimum point on your graph. And that's really what we're going to talk about here, is that these, you know, critical values are possibilities of where we could have what we call relative extrema, or relative maximums and relative minimums. So we're going to write this out as a definition, and then we'll talk about how we use it. So let me write this out here. Another definition. So a lot of definitions in this section to start. Having an understanding of them will help you understand how to graph these later. So for this definition, if I said I had f of c, right? So f of c is a relative minimum. And sometimes instead of relative, they might say local. Right? So local or a relative minimum if f of c is less than or equal to f of x at all values of x near c. So the first thing is that this is local. So when we call it a local minimum or a relative minimum, what we're really saying is, you know, there could be other places where there were maxes or minimums. It doesn't have to be the absolute one, meaning it doesn't have to be the lowest point on your whole graph. What it's really saying is that it's a dip in the curve. Like you'll go downward and then go back upward. When we write this f of c, this is the original function evaluated at that point c that we said was a critical value. All right, and it's saying that f of c is less than or equal to f of x. This is just saying that f of c, the y value here, is smaller than all the other y values near it. That's what this definition really says. And if I was to draw this, just to kind of give you an idea of what you'd be looking at, you know, if this was x and this was y, I could draw a graph in here. We'll call this f of x. And I'm just going to label these points. You know, here's C1, here's C2, here's C3. And I just want to kind of point out what's happening there. So, where would we have relative minimums? Well, you would have relative minimums anywhere that you went, for all the c values, right? The y value is lower than all the y values around it. In other words, where you're going to have this low point in your graph and then go back up, right? So here at c1, right, it's going downward then come back up. This value, f of c1, is lower than all the ones that are close to it. It's not the lowest value on the whole graph, right? But it's a relative minimum. So this would be a relative minimum, right, at c1. Where else would you have one? Well, at C3, right, it's going downward then come back up. It's the low points, right? So this is also a relative minimum. And now we can also talk about relative maximums, where the graph is going upward and then coming back down. So kind of like a peak. It's the same type of definition, right? So f of c is a relative maximum. Remember, we could say local. Relative and local are the same word here. If f of c, right, so if the y value right here at c is greater than or equal to f of x at all values of x near c. In other words, all the y values close to it are lower than the y value you see here. So f of c is the y value. It's saying all the y values that are near it are smaller than it. Well, that's what really is happening at like point C2 here, right? This is going to be a relative max. In other words, all the y values close to this y value are lower than it, right? F of C2 is higher than the ones that are near it. That's what this near means in our definition. It doesn't have to be the absolute max, right? It's not the highest point on the whole graph, right? These arrows mean it goes up forever. It's just the highest point in a local region, right? So it's where you have peaks in your graph. So where do these occur? Well, these occur where you have critical values, right? So the critical values are these c values I'm talking about, where the critical values are a possibility of where a relative minimum or relative maximum could occur. It doesn't mean it definitely has to, but it means it could. So our theorem that we're going to write here, and then we'll do some examples, really says this a little more explicitly. The theorem says a function f of x has a relative extreme value. When I say relative extreme value or relative extrema, we're talking a relative maximum or a relative minimum. If f prime of c equals 0, or f prime of c does not exist. So we're talking about this same critical value c, right? So the critical value is where we could have a relative extreme value. That's what this c is here. So just making it clear, i.e. relative extrema, meaning relative maximums or relative minimums, relative extrema occur at critical values, right? That's what this really is saying. Now, it doesn't mean that if you have a critical value, you automatically have a relative extrema. You have to test to see if that's true. But these are the locations where they would occur if they exist, these relative extrema. They only occur at the critical value. You're not going to find relative extrema at other places. So that gives us a way to approach this, because basically what this is telling us, and we'll show this in an example in a moment, it's really saying that if you have a function, right, f of x, if you take the derivative and you find the points where they have critical values, so where the derivative equals 0 or where the derivative doesn't exist, then you can check those values to determine if they are maximum or minimums, relative maximum or minimums, right? So relative extrema. So we'll do an example here, and then we'll talk about what we call the first derivative test. So for this example, determine the critical values for this function f of x equals x to the third power minus 9x squared minus 48x plus 52. All right, so we're going to try to find the critical values. Well, where do the critical values occur? The critical values occur when the first derivative equals 0 or the first derivative doesn't exist. So before we do any of that, for our solution, the first thing I got to do is find the first derivative, f prime of x. And we can do that, I think, fairly easily. You should know the derivative rules at this point. F prime of x equals derivative of x cubed is 3x squared minus the derivative of 9x squared. 2 comes down, 2 times 9 is minus 18x to the first power, and then minus 48x. The derivative of that is just minus 48. Derivative of 52 is a constant, it goes to 0. So the next thing you want to do is make sure when you're trying to find critical values, there's two things you're looking for, right? You're looking for either where the first derivative equals 0 or where it's undefined. Well, when I look at this, you know, there are no places where the first derivative doesn't exist, right? For this polynomial, it's defined at all x values. In other words, the domain of this is all real numbers. So we don't have to worry about the part where the first derivative doesn't exist. So what I am going to do, though, is I'm going to set f prime of x equal to 0 and solve for x to find the critical values. Because that's really what you need, right? So we set f prime of x equal to 0 and solve for x to find critical values. So I'm really setting this 3x squared minus 18x minus 48 equal to 0. Now we should know how to solve this. You know, we reviewed this before. You can solve this by factoring is the easiest way if it does factor. Otherwise, you know, you do know quadratic formulas, another way to get there. But the first thing you should always do is try to factor, because that's going to be your first line of defense. So 3x squared minus 18x minus 48, we're going to factor out a GCF of 3. That leaves us with x squared minus 6x minus 16 equals 0. And then the 3 in front, you know, stays in front. You don't actually use the 3, but I'll just keep it in front so you see it. So you have 3 times. Now x squared minus 6x minus 16, if we're factoring that, x squared is x times x. We want things that multiply to negative 16 and add to negative 6. Those numbers are negative 8 and positive 2. You should know how to factor this. And then to solve this, remember what you do. You set each of the factors that contain a variable equal to 0. But 3 isn't one of your answers. 3 doesn't equal 0. Remember, when we do this, we're trying to figure out what numbers multiply together to give me 0 here. Well, 3 will never be something that multiplies to give you 0. So 3 doesn't equal 0. It's out. You don't even have to use it. But I just want to make sure you understand 3 is not part of your solution. You set x minus 8 equal to 0. You set x plus 2 equal to 0. And you're solving this. And you've solved these types of equations before. We add 8. We add 8. So we get x equals 8. Here we subtract 2. I get x equals negative 2. So 2 answers, right, in this case. Doesn't always have to be 2 answers, but there's 2 answers here. What were we finding? We were trying to find critical values. So these right here, x equals 8 and x equals negative 2, these are the critical values. Now, what does that tell us? Well, that tells us that these are candidates for points where we could have a maximum or a minimum, right? A local max or a local min. The relative extrema could occur here. Doesn't mean they have to, but they could. So the next theorem really talks about this. It's the first derivative test. So we'll talk about the first derivative test, then we'll come back to this and we'll talk about how to apply it here. So the first derivative test is really what this section is about. And, you know, I'm going to write it up formally, but really it's more of a process that you do. This formal definition part is just kind of telling you what it actually is and how it works. So the first derivative test. And what it says is, suppose f of c, or sorry, suppose c is a critical value for f. Right? So suppose c is a critical value for f. So like we just found, we found critical value. So suppose c is a critical value for f. If f changes from increasing to decreasing at c, then f has a relative, and let's talk about what it is. So if f changes from increasing to decreasing at c, think about what's happening here. So first off, c is a critical value, so we know that the derivative either equaled 0 there or it was undefined there, right? That's how we found the critical value, just like we did a minute ago. So if I'm going from increasing to decreasing, think about what's happening with the graph of f. It's saying it's going upward, then it's going downward. So if I'm going up and then coming down, what kind of relative extrema do you think I'd have there, a maximum or a minimum? Well, it's going up, then coming down, so that kind of shape would be a maximum, right? So that'd be a high point. So it has a relative maximum at x equals c, right? So at that critical value. And, you know, we're going to talk about how you find this in a minute, but we are going to use the first derivative to help us, right? Because if we can find where f prime is positive, we know the original function is increasing. If I can find where f prime is negative, I know that's where it's decreasing. So that's how the first derivative test is going to help us do this. Similar but different, if f changes, right? So if the original function changes from decreasing to increasing at c, think about what that means. The original function is going downward and then it's going up. If I'm going down and then coming up, what kind of point do you think I have, a maximum or a minimum? I'm going downward and then coming up, it's going to be a relative minimum because it's a low point. So then f has a relative, remember, or local is another way of saying that, a relative minimum at x equals c. So that's the first derivative test tells us. Notice I didn't actually even talk about the first derivative here, but I said it out loud and I'll mention it again, right? If I'm going from decreasing to increasing here, that means that if I have the original function decreasing, what has to be true about the first derivative? Well, the first derivative would have to be negative. So if I can find where f prime is negative, then I know where it's decreasing. If I can find where f prime is positive, that's where I know it's increasing, and that's what's going to tell me where the minimum occurs here, or if the maximum in the opposite order. Now, we'll talk about how to use the first derivative test. It's really saying that the critical values are giving you these boundaries where they know that the function isn't, or that f prime isn't positive or negative. It's either undefined or 0. So then we can check to the left and right of those to determine what's going on with the rest of the intervals. So we're going to use the same example we just had a minute ago. So if I said determine all relative extrema for, and I'm going to write the same function I had. So for f of x equals x to the third minus 9x squared minus 48x plus 52. Okay, so it's the same function I had a minute ago. It's a different question, right? The function I asked in the previous one was to find the critical values, which we did, right? We found the critical values are going to be 8 and negative 2. So if I'm trying to find all the relative extrema, the first step is, right, first find all critical values. Remember, the critical values occur when f prime of x equals 0, or when f prime of x is undefined, does not exist, and in the last example, we did this. So I'm not going to redo all that work, but normally this would be your first step, find the critical values. So we did this in the last example. And we have that, when we did it, we said take f prime of x and set it equal to 0. Because I'll write out what f prime was, because that's going to be important to us, right? We had f prime of x equals, it was 3x squared minus 18x minus 48. And then we had set that equal to 0. The critical values we got from that, right? I'll use CV for critical values. The critical values that we got from that were x equals 8 and x equals -2. So that part's already done for us, but if not, and I asked you to find the relative extrema, the first thing you want to do is find the critical values. So we did it there. The next thing you want to do is use the first derivative test to figure out where the maxes and mins occur. So now I'm going to use FDT for first derivative test to determine if any relative max or mins occur at the critical values. Now, the way we do this, I'm going to draw out a number line. All right, and on the number line, I'm going to put the critical values. So here's my number line. It's a number line for f prime of x. All right, and that's important to know when we're doing this. So we're going to call this f prime of x the number line. And you want to put your critical values on there in order that you would normally have them from left to right, lowest to highest. So I'm going to put -2 here, and I'm going to put 8 here. And what we're going to do is, you really want to test values to the left and right of each point, right? So we're going to test values in f prime of x to the left and right of each critical value. So let's talk about what values I would test. Now, it doesn't matter what you pick. You can't pick the critical values themselves because we know that that's where the function, the derivative is already equal to 0. So let's try something to the left of -2 here. So I'll say let's try f prime of 3, or -3, sorry, right? F prime of -3, something to the left of -2. All that means is that I'm subbing this into my f prime of x function here. So it'll be f prime of -3 would be 3 times -3 squared minus 18 times -3 minus 48. And when I do that, you're going to evaluate it, right? This comes out to, this is 3 times, -3 squared is 9 times 3, so it's going to be 27. Negative times that makes that positive. 18 times 3 is 54. And then minus 48. And we want to figure out what this value is. Ends up being 27 plus 54. What's that? 81 minus 48 gives me 33. Now, all I care about, and this is very important, the thing I care about when I do this is that if the first derivative is either positive or negative here, because I'm looking to see where it's increasing or decreasing. So the actual number you get doesn't matter. The sign of the number matters. So 33, well, that is positive. So I'm going to put a little plus sign here, right, to the left of -2, because that's where -3 was. That means any value I would have substituted in to the left of -2 would have given me a positive number here. So if I chose -3, that's fine. If I chose -1000, that would be fine, right? It doesn't really matter as long as I'm picking something to the left of -2. I get the sign that goes along with those values, which is positive. Well, what's that tell you about the original function? Well, it tells you that if the first derivative is positive, right, the slopes are positive for the tangent line, that tells you that f of x, the original function, is increasing, right? So the first derivative being positive tells you the original function is increasing. And then we do this for this next part of the integral. So we're going to look at f prime of a number between -2 and 8. I'm going to pick 0 is usually the easiest one to use. You can pick any number between negative 2 and 8 though. Well, f prime of 0, what's that equal to? Well, it'll be 3 times 0 squared minus 18 times 0. Make sure you're substituting into f prime and not the original function, right? And then minus 48. So this ends up equaling negative 48. Well, what do I care about? What's important? The sign. This is a negative number, so it's negative. So I'm going to put a negative sign here between negative 2 and 8. That's telling me f prime is negative between negative 2 and 8. That tells me the slopes of the tangent lines are negative between negative 2 and 8. Well, if this is negative, that tells you that the original function f of x is that either increasing or decreasing. Well, negative slopes tell you it's moving downward from left to right. It's decreasing. So the first derivative being negative tells you the original function is decreasing there. And then we'll do this for a point to the right of 8. Let's use f prime of, let's say, 9. Doesn't really matter what you pick. We have 3 times 9 squared minus 18 times 9. Again, make sure you're substituting into f prime. And if you evaluate this, 3 times 9 squared minus 18 times 9 minus 48, you could do it on your calculator. This comes out to 33, which again, I only care that it's positive. It's a coincidence that these numbers are the same. They won't always be. But 33 is positive, so f prime is positive everywhere to the right of 8. That's what it's really telling me. It doesn't matter what value I picked, f prime of 10, f prime of 1,000. Wouldn't matter. As long as I pick something to the right of 8, I'll get a positive value for f prime. And then again, we ask ourselves, well, if the first derivative is positive, what's happening to the original function? Well, f of x, that would be a positive first derivative is positive slopes, so the function would be increasing, right? A positive slope tells you it's increasing. So we did all this to determine what was happening to the original function f of x. And then you have to figure out, are these relative maximums or relative minimums, or neither? They could be neither. And for this case, right, taking a look, let's say what happens. F of x is increasing, so that means it would be going right here. It's going upward, and then f of x decreasing means going downward. Well, if I'm going from going upward to going downward, this is giving you information. It's telling you that if this is going up and then coming down, that's a peak there, right? That's a high point, so this is going to be a relative max at x equals negative 2. All right, and then think about what's happening here. You're decreasing, right? So you're going downward, and then f of x is increasing, you're going upward. So if you're going downward and then upward at 8, you're going to have a relative going down then up. Right? What happens if you're going downward then upward? You're going to have a relative min, right? Relative minimum at x equals 8. So you're using the information about f to tell you what's going to happen at these points. Right? So we have a relative maximum at x equals negative 2. We have a relative minimum at x equals 8. Now, this is where they occur. We also need to find the y values that go along with it, right? So we have to find the corresponding y values to determine the actual heights of these, because the actual maximum and minimum of the functions are the y values. They're the f of c values. So when you do this, you found where they occur. Now you're going to find the y values that go with this. So now I'm going to find corresponding y values. So we'll do that. I'll do it on the back of this page. We have our original function, which I'll rewrite, and then we'll look at what happens there. So we have the original function, right? So we want to sub into f of x equals, it was x to the third power minus 9x squared minus 48x plus 52. And when you do this, you want to test each of them individually or substitute each of them individually in there. So f of negative 2 would be negative 2 cubed minus 9 times negative 2 squared minus 48 times negative 2 plus 52. Make sure you're subbing into f of x now, because now we're looking at the original function and trying to find the y values there. And when you multiply this out into your calculator, you can type it all in if you have a calculator displays it on the screen. If not, you'd have to do it term by term. Make sure you have parentheses where you need it. So parentheses -2 raised to the third power minus 9 times -2 squared minus 48 times -2 and then plus 52. I get 104. So, this point is the x value comma y value. It's -2, 104. And then similarly, you can sub in f of 8 to determine the y value there. F of 8, it would be 8 cubed minus 9 times 8 squared minus 48 times 8 plus 52. And if I type that all in, you could go up here and replace what you had. Like if you know how to reinsert that to the line before, you can just hit up and move to it and then change all those values that you had -2 into 8s. We get -396. You could also just type the whole thing out again. So the point x comma y, 8, -396 is on my graph. So what we know is, let's just go back a page just for a second. We know that we have a relative maximum at x equals -2. We know that because f of x was increasing, then decreasing, from the left side to the right side. So it's going up, then coming down. Well, if you go up and then come down, there has to be a maximum. There has to be a high point. So when I say the relative max is at x equals -2, when I go to write this, the actual relative maximum is 104. It's the y value I'm talking about. So from this we say the relative maximum is 104. It occurs at x equals -2. And you might see this written as a point, right? So you might see it as the relative max being just listed as -2, 104, but have an understanding that the y value is actually what the maximum is, right? So the relative maximum is the 104. It occurs at x equals -2, saying the highest y value locally there is 104. And similarly, but different, at x equals 8, it was a relative min because we were decreasing and then increasing, so you're going downward then coming up. So what happens if you go down and then come up? Well, then it's a low point on your graph, which makes this a relative min. So when you talk about this, right, going downward and then coming upward, it's a relative min, so we know we have a relative minimum, right? So the relative minimum is the y value at 8, so is -396. It occurs at x equals 8. You might also see this written as an ordered pair. Relative minimum, we could say it has coordinates 8, -396, but again, remember, the actual minimum itself is the -396. We call these relative maxes and relative minimums because they're not necessarily the absolute maximum or minimum. It's the highest or lowest point locally when we talk about relative max or relative min. It's where the graph peaks or it has a valley. And we could talk about how to graph this, and we will a little bit later. But you should have an understanding of where these are. How is to just draw a quick sketch of this. And this is not something I'm asking for the problem, but just kind of to give you an idea of what it would look like, right? And this is, we don't have a grid that's going to have 100 and 300, 400 types of values on there. So I'm not going to put all the tick marks on here. But let's just talk about what happens. We had at -2, we are up at a value of 104. So let's just say this is 104. So -2, 104 would be a point there. At 8, we are down at a value of -396. So there'd be a point down here. Now, we know at -2 is a relative max. So I know the graph would be going upward and then coming downward there. At 8, I know it's a relative min, so I know it's going downward and then coming upward. We actually see this in what we wrote, right? F of x is increasing, then decreasing as you approach -2. So you're going up, then coming down. And at 8, you're going down, then coming up. Now, in between here, there were no other critical values, so you're not going to have any other maxes or mins, you know, following through there. So if I say it's decreasing between -2 and 8, it's decreasing that whole way through. If I say it's increasing to the left of -2, it's increasing that whole way through. If I say it's increasing to the right of 8, it's increasing that whole way through. So I know I'm increasing all the way up to -2. Because it's a polynomial, I know it goes on forever in both directions. So, you know, you'd have something that looks like this. This is increasing as you approach -2. Right? It's going downward to the left forever, but it's from left to right, it's increasing. You get to here. And then you want to get down to, now you're decreasing because it was a relative max. You want to come down, decreasing until you get to 8. Now, we know something about this. We know the y-intercept is at 52. We'll talk about that a little bit later, but when x is 0, the y value you get is 52. So let's say it crosses at 52. So you got this graph that does this, and you know it's going to come down here, and it's always decreasing until you get down to 8. 8 was a relative min, so then you know it has to go back up, and it's going back up. Well, it's increasing forever after 8, right? There were no more critical values, so f of x is increasing forever after 8. So this is a rough sketch of f of x, and a lot of times we'll ask you to just do a rough sketch. You know, we won't ask you to be too accurate, but you know, you should be able to find the y-intercept. You should be able to plot the relative maxes and relative mins. Notice that these are relative maxes and relative mins, not absolute. Absolute would be the highest or lowest point. We'll talk about those later. It's not absolute because this graph can go up forever, so it's not an absolute maximum. This is not an absolute minimum because this graph is going to go downward forever. So the y values for a range on this are all real numbers, but we are finding where the relative maxes and mins occur.